Hey guys, today we're looking at question 22 for LeetCode. The question says, given n pairs of parentheses, write a function to generate all combinations of well-formed parentheses. Now what does this mean? So suppose we have an input n equals to 2. What we've been asked to do is output an enumeration, so a list of strings where each element is a string of parentheses that is made up of 2 pairs of parentheses, and the overall string is well formed. So this could be its output for the case where n is equal to 2. What does it mean to be well formed? Well, suppose you have a string of parentheses called x, then x must start with an opening bracket, and it must have a closing bracket somewhere within it such that it splits the remaining characters into a string y and a string z, where y and z are well formed. So suppose x were to look like something like this, then certainly x starts with an opening bracket and it has a closing bracket somewhere within it so that it splits the remaining characters into a string y and a string z, and as you can see, both of these are also well formed. Just as a note, the base case for this definition would be an empty string. So if y or z were to be an empty string, I'm just going to denote that as 2 quotes, then this is trivially well formed. So if you had a scenario where x equals something like this, then yes, it's still technically split up into a y and a z, where your z is just the empty string, so as such. So now let's talk a little bit about the solution. My solution to this problem is a recursive one. At each recursive step, which I'll denote rs, we're going to ask the question, given a substring s, what can we append to s? Of course, the characters we can append are either the opening bracket or the closing bracket. So if s were to equal something like this, we're simply asking what can we add next? And it must be one of these 2 characters. Now let's draw out what our recursive tree might look like. At the top level, the root of the recursion will look like an empty string. We'll branch out into 2 subproblems, the first one being the result of adding an opening bracket, and the second one being the result of adding a closing bracket. Then at each of these subproblems, we ask the same question. Given the opening bracket, what can we append to this string? The answer is, of course, the same. We can add another opening bracket, or we can add a closing bracket. Similarly, for the right-hand side, we can add an opening bracket, or we can add a closing bracket. I've gone ahead and drawn the entire search tree for the case where n is equal to 2. The leaves of this tree describe all possible combinations of opening and closing parentheses that would fit on a string of size 4. Although the leaves here are not the solution we want to ultimately output, observe that the solution we need exists as a subset of the leaves, and I'll highlight those leaves below. So the question then becomes, does there exist some kind of a computation we can do while processing this search tree such that it outputs only the leaves that we need? We can achieve this during the recursion step of our algorithm. Given an internal node, suppose this one here, let's ask the question, is it possible to extend the characters of this string to create 2 pairs of well-formed parentheses? Now, how might we assess such a thing? Well, at the very base case, we can count the number of opening brackets. In this case, we have c is equal to 3. We know that it's not possible to create 2 sets of well-formed parentheses as we already have 3 opening brackets. This would require us to create, at a minimum, 3 sets of well-formed parentheses. Or more precisely, if the number of opening brackets exceeds n, then exit. Let's consider another internal node, for instance this one here. Now it has one set of opening brackets, so that seems to fit the bill. Now let's count the number of closing brackets. It has 2 closing brackets. Now clearly, if it's already got 2 closing brackets, there's no way we can extend this set of characters to create a pair of well-formed parentheses. As it's already got 2 closing brackets, it must have at least 2 opening brackets ahead of these brackets to be able to form a set of well-formed parentheses. More precisely, if the number of opening brackets is strictly less than the number of closing brackets, then we can also exit. Now let's execute these rules on each of the internal nodes and see what that does to our tree. Let's start at the left-hand child of the first node of the root. Well, the number of opening brackets is 1, which is clearly less than n, so that's fine. And the number of opening brackets is strictly more than the number of closing brackets, so we can keep this node. On the right-hand side, the number of opening brackets is still less than n, as 0 is less than n. However, the number of opening brackets is strictly less than the number of closing brackets, as 0 is less than 1. So at this point, we can exit the recursion, and we no longer need to search the remainder of this search tree. So by doing this, we've effectively pruned half of the search tree. Similarly, the nodes here and here, as well as here and here, all satisfy the conditions for the recursion to exit early. If these nodes are internal nodes, then we never reach the leaves of these subtrees to enumerate, and if they're already leaf nodes, we simply ignore adding them to our end enumeration set. Therefore, you can see that the only leaves we actually process are the ones we are interested in. Alright, let's do some programming now. We've got the solution put together. I'm going to write this up in C++, but feel free to do it in any language or follow along. The implementation details will be largely the same, just the semantics will change depending on which language you use. So first thing I like to do is just to find a method outside of like the parent method that they give us. So create paran, this will be the recursive method that we call at, when we explore this search tree. Now in our solution, we defined some checks at the recursion step. So let's create a section here in the code where we'll do those checks. You might remember we had the number of opening brackets, and I'll call that variable L, and the number of closing brackets, let's call that R. So the check was if the number of opening brackets was strictly less than the number of closing brackets, then clearly we can't create any more well-formed sets of parentheses. And our other check was if the number of opening brackets was strictly more than the number of pairs we're trying to create, then we could also return. So yeah, we need another variable here, number of pairs, n. Or actually, let's call that n start, because I have a feeling we will need a different variable n. And then we also actually define a base case for our recursion. Not a base, a base case. And what is the base case? Base case basically tells the recursion, we are at a leaf, stop recursing. For this, what I'll do is, this is where I'll introduce a variable n, and n is just going to be a variable that's indicating the depth of the search tree, and we will decrement it every so often. And so once n is equal to 0, we'll know that we are at a leaf and that we should do something. We can talk about that in a second. So that handles the checks and the base cases. What are we actually doing at each recursive step? Well, we're going to have some kind of a substring. We're going to have some kind of a start of a string. Let's call that string p. And we said that we were going to recurse into 2 different subtrees. One subtree where we append an opening bracket and another subtree where we append a closing bracket. So let's first start with the opening bracket case. We have our string P and we want to append, so in C that's push back, we want to append an opening bracket to this string. And then we want to actually recurse on this, method, and it'll yield some solution, but ultimately we're going to exit from this recursion and we're going to have to pop what we just pushed onto this string. So we want to remove that open bracket, and we want to remove it because now we want to try the other option where we add a closing bracket instead. So very similarly, all right, great. Now we don't actually have to return anything after the recursion has happened because all of the work we do, all the enumeration, that's done at the leaves of the tree. Now, let's consider what we do in our base case. So we have our base case, we can expect, well, we haven't returned yet, so we must be, we must have some string P that is correctly created, and now we just need to store it so that we can access it later. So suppose we have also got some vector of lists, our enumeration list, I'll call that out, and we just want to push back the value of the string. So we want to add the string to this vector. All right, great. So from here, we could also return. Fantastic. Now let's define some of our variables for the function signature. What did we say? So we have this string P, we have an n start, we have an n left, right, I don't know why I said that, and our list of strings, and we'll call it out, and we'll pass it in by reference. We don't want to create a copy at every stack. All right, great. Now we can have a look at the parent method. To generate parentheses, we'll call create paran. Let's create our list of strings. I'll just call it out again. And we'll call create paran. What did we say? Our root node will just be the empty string, right? So we can just pass in an empty string into the root level call for the recursion. Our n start will just be the n that we're passed in from the parent method. Our n again is n, and L and R we can set to 0 and 0, and pass in our list. Fantastic. And then finally we want to return our list. Okay, that looks all right. Whoop, missing a couple semicolons there. Oh, that's a colon. Great. All right, let's execute that, see how it goes. Oh yeah, so we haven't actually provided any variables into our recursive call. So obviously we want to pass in the string in its current form. Our n start stays the same. Keep n the same for the recursion call into the open bracket. Since we've added an open bracket, we want to increment our L variable. Our R variable stays the same, and we pass in out. So then we exit the recursive call. We kind of reset, we remove the open bracket and we add a closed bracket instead. We pass in this new modified P. Our n start variable is the same. This time we want to decrement n1. And keep L the same and increment R. So let's try this out. Okay, that's great. Seems to have worked for the 2 test cases, and I'll just submit that now. All right, cool. All right, so that seems to have worked. So that's the end of the video. Thanks for watching, guys. Stay tuned for more. See you in the next one.